I'd like to introduce the last speaker of the day, and the speaker is Piotr Padlewski. Piotr studies IT. He works for this company called IIIT. He works with Clang, and interestingly, he used to work in Google for a while with Chandler's Caruth's team, Chandler, who you met earlier today. And Piotr will be talking about two things. The first one is thin LTO, scalable and incremental LTO. And the second is C++ what. Let's have a big hand for Piotr Padlewski.
Okay. All right, so yeah, on this presentation, I'm gonna talk about the thin LTO, which is a project that I work on the last internship. And I borrow slides from the keynote of LLVM dev meeting. So this will be like a shortcut. If you want to know more, just watch the keynote. Thin LTO, we want to get to the LTO as something that will be enabled by default. But let's start with what is LTO. So LTO is a link time optimization, and basically we want to get out of the barrier of the single translation unit. So we want to do optimization across different modules. And if you do LTO normally, it works like this. You just have these normal files, and if you compile it normally, then you will get these object files like elf, maho, or coef, dependent on your platform. But if you specify a FLTO, then you will get this nice LLVM IR. So this will be a LLVM bitcode. And it still will be in the .o files, but the linker will know what to do with them. How does it work? You firstly generate those object files, which is a bitcode files. And then you have a linker that knows about it. It has for example, if you use Gold, it will have a plugin. You take all the bitcode files, merge into like giant, very, very giant bitcode file, and then you just do a bunch of optimizations on it. And then you could have a code gen that is parallel, and then you have traditional linking. So why we care about LTO? Binary size. We could get a smaller binary size because of internalization. Because if we know that there is a function defined somewhere and we just inline it everywhere, we can get rid of the definition. Second thing, performance. 10% performance, sounds very good. And this is because we can do inlining across modules and another fancy cross-module optimizations. And as you can see on benchmark, some benchmark are getting pretty nice, 90% faster. And as you can see here on the top, we have a single source. So LTO does even make sense if we do it on a single file. And this is because of the internalization. Just linker, the optimizer can assume that it see all the functions that are called. So, but there is no free lunch for a LTO. There are some problems with it. After 10 years, nobody see whoever used LTO in a production or ever tried. I see oh yeah, 3% maybe. So the problem is that it's terribly slow. If you can compare building of a Clang, LTO to non-LTO, this is terribly slow. Also, it is not incremental. If you just fix small typo and recompile it, then you will get 4 seconds on a normal build and almost the same thing on the LTO. And the last, which is the hardest thing, is this is a memory hungry. Starting from LVM 3.6, we got lower, but it's still 11 gigabytes. This is madness. And for some projects that are much more bigger than Clang, this is dead end, because we are just compiling. We are having 2 hours with more than 50 gigs of memory, and it just crashes. So in order to fix that, we need something that is parallel, incremental, and it's not that memory hungry. So thin LTO. So it was designed for a very huge application, like a Google scale applications. And the first design was that we just have this normal compile, and we would like to have these parallel backends that we would just could do the optimizations in parallel. But we need this small thin layer of the synchronization after generating bytecode files. So how does it really? And because it is all parallel and like those backends are not connecting to each other, then they are incremental because we can just run single backend that changed. And it works by using information from another modules only that we need. It doesn't like need to have the whole binary, like every LVMIR line of code to do this. So how does it work? So we generate this in parallel. We generate bytecode files, but we add some very small summary, and then linker takes this summary, build a index which is not pretty big, and because of that, we don't need to parse LVMIR, which will be very slow if we would do so. And then based on the index, we can do importing. We can just take function that we need, like for inlining and for some optimizations, and just import it, the modules that we care. And then we can just run our boring optimizations, backends, and traditional linking. So we would have this small summary, and in the summary there will be like very info, like for each function, what are the functions that it calls and what's the size of the function. And with PGO there will be also like hotness of the call sites, etc. So what is the performance? Like starting from the LTO, just the link time for a client will take like 1,000 seconds. And if we take a fin LTO in one thread, this will be 20% slower. And this is because fin LTO is actually doing a redundant job there, the redundant work. So, but if we have more threads, then as you can see, it will be much faster. Like if we will get to the 16 threads, which should be like, you know, a normal machine that we should have under the desk, then we will get like 15x faster. And what about memory? Like with single thread, we will get 17 times less memory. And going more, as you can see, it doesn't grow that much. Okay, but this was the release. What about if we have some debug information? So, as you can see, with one thread, we will have that many, and then this won't grow that much. So what about the debug? Like the debug is very huge, right? So for LTO, it will take like 70 gigabytes, right? This is madness. And for fin LTO, only like half a gig. And then, as you can see, this scales very nicely. Okay, so GCC also has something similar to fin LTO, but and it's called Whopper. So it's pretty much doing the same thing, but a little bit differently. But it has those two steps. So let's look at those projects and see how, like, this is the conversion of the size of the projects, right? On the nodes on the edges. So add delivery and the Chromium is pretty big compared to Clang. And if you look at the peak memory, like the best thing that GCC has will be killed after taking like, 2 hours and more than 12 gigs of memory. And so what about the incremental build time? With a clean build, it will be like 25% slower than a normal build. If we change something that is widely used everywhere, then we should recompile it everywhere. So it will be very similar to a normal build. But if we just change very small thing, like a typo, normal build will be very fast. And monolithic LTO will be very slow. and final LTO will be there. So it's very, very close to the normal build. And this is the performance on the spec. As you can see here, you have some peaks of 16%, usually like 10 or 8%. It usually just meets what LTO can do. So the conclusion, final LTO scales as regular non-LTO build, performs very close to monolithic LTO, and it's very incremental. So it would be very, very nice if this would be like as default. It would replace O2 and O3. Okay. Thank you. Okay, so my second talk. On this talk, you won't learn anything, right? Okay? It's like this. You know, I hope you like the quiz that was on the previous presentation. This will be like a short quiz, but you won't learn anything useful. And second warning, all the code snippets compiles. But so, just don't worry. I'm from the internet, so let's look at this code. I told you that every code compiles, right? Like this looks very suspicious. But let's open it in something that's not IDE. It actually looks like this. As you can see here, you have some Unicodes there, and there is some special Unicode that is 0. It doesn't have any length. It's a space that doesn't have any length, so it looks like that. And this is actually a C++ 11 standard compliant. It's like you can write this code. Like really, like what? Okay, there is this rolling joke in a C++ standard that everything that is uniform is more like unicorn, like uniform initialization or unicorn call syntax, right? So there's a guy that actually using this Unicode that wrote this, and yeah, what? And like I'm just waiting till like people will write code like this. This is actually the Ruby code, like just flip the table. And if you want to be very classy, you can also write code like this. So yeah, very classy. Okay, what about standard versus compilers? So I just took this screenshot from the standard of C++ 14. But this is actually, I think it was modified since '98. And if you take GCC, like GCC 6.1, it actually won't compile. It's like, come on, this is something that is like 10 years old and you still cannot compile it? And like, really? So let's look at some other codes. Does anyone see a error here or bug? So, okay, maybe I will have with this. Yeah, there is just start comment there, right? There is no division. And like, this sounds kind of boring because, everyone is using IDE, have code coloring. What about this one? Well, what does it do? It actually doesn't do anything. It is empty lambda call of empty lambda inside the lambda, but using digraphs. And it's like if you show it to like Java programmer or something, it will be like, oh my god, this is C++. It's like, oh, help me, right? And I have pro tip for you. If you have code like this, you can also change it to have something like this. You will have the same semantics. Like those two codes will do pretty much the same thing, which is nothing. And this is because you can actually get rid of if you don't have any arguments, then you can get rid of these two params. And there is also this running joke about lambdas that this is a way how to use every like bracket, right, to define function. So yeah. Okay, there is also this thing, and actually I think this is very, very useful. Like not many developers know about it or use it. You can actually write or and and instead of these ampersands. And I actually think that this looks much better, right? Because maybe because I like Python, but let's with every feature comes great responsibility. So like as you can see here, like what is doing? Like, I have some variable that its name is bitend, and I'm just using it in some weird way, like this. And I actually don't have any variable name. This is just a ampersand, just in a keyword. So I am actually have const reference to int, and then I am just taking a address of a foo. And what about this one? This one even looks much better because I have argument that is final and override, and actually the function is deleted. So you can actually use this final keyword like everywhere. What? Okay, have you ever thought about like how you can write one simple type, right? Like for example, this unsigned long int that is constant volatile, and the name is of course final. So, but I'm missing some keywords here. What about this thing? Like, and you can actually also in this one you can just permutate every token, and it gonna work. And okay, thanks to Chandler. What about this one? Yeah. We spent a couple of minutes to make it compile. What? But as I said, with great features comes greater possibility. So you can also write code like this. Like, does anyone know what it's doing? So, okay, I can walk you through. So I have this car array, and this is this D graphs. So here I'm taking value of one car, and then I'm using this. This is not I. This is actually the operator, right? And then this exclamation mark starts. How it's called? It's ternary operator. And in ternary operator, I can put a throw, or I can put this thing. I don't actually know what is. Oh, I don't remember what it's doing. I remember putting this there, but this is. Oh yeah, this is an empty lambda. That's of course, yeah. That's all I have. So yeah, and this is what I like in the C++ programmers. Like if you show this kind of code in C++, like yeah, I'm just stuck with this. Like I will just use it, right? Okay, thank you.